All right, welcome back. It's time for Chapter 5. We're going to talk about right angle triangles and the associated calculations that you can do with them. So, in the previous chapter, we went full force on the Pythagorean theorem. Now it's time to invest some energy in sine, cosine, and tangent. So, I just like to say that there are many of you that may think, we're covering some basic material here. But I'd like you to keep in mind that there are people in the program and people that I have taught over the years that haven't been in school for many years. Or perhaps they're learning math right now and it's not their first language in English. So I really want to emphasize that it's not just about the learning experience in terms of the content. It's about getting everybody up to speed on the material and improving the quality of the learning experience in your program. Making sure that you really understand the math that you need to know, especially in your program. So let's get going on this. So we're going to go through the course notes. This is in Chapter 5, and it's pages 1 to 14. So today's lesson is not going to be too intense in terms of difficulty. It really is building a foundation so that next week we can tackle many application questions, and the week thereafter also even tougher questions and more practical. So we left off last time saying that I would introduce sine, cosine, and tangent. So what are these quantities, or what are these things? And I really just want to get into creating a framework to explain it better for you. And that is the purpose of today's lesson. So, in order to deliver and explain what sine, cosine, and tangent are, you first really need to understand that you have to label the sides of a right angle triangle. And once you have that labeling in place, we can actually create, or define, I should say, the ratios. So, if you go to page 4 of the notes, you'll see this example number 1. And we're going to just cover these three triangles here. We're going to label the triangles. But I want you to make an important emphasis here. It's relative to the indicated angle. So the angle that's indicated varies on each triangle. So these are the angles that we're interested in. Because depending on the angle that you choose, the relative labeling will change. So let's take a look at each of these separately. Well, relative to the angle, one of these sides will always be labeled a specific way, and it's insensitive to which angle we have. Whether you choose this angle here or this angle here, the labeling of the hypotenuse is always the same. So let's just write there hypotenuse. Hypotenuse. So, relative to this angle, this side is opposite. And the side that is over here beside the angle theta, we need to give that a name. We could call it beside, but what is typically named is the adjacent side. So the word adjacent just means beside. So that's pretty much it. Now, if you don't want to label with full words here, you don't have to. So I recommend maybe that we follow this convention. How about I put H for hypotenuse? And I'm going to put a box on it. I'll put O for opposite, and I'll put A for adjacent. The box isn't necessary, but imagine if you're writing in a single color, like a blue pen or something, you don't want to get all colorful on the page if you don't have a lot of time to invest in terms of each question. So that's why I put a little box around each of them, just to emphasize that it's just a label. So take a look at this question. Before we even care about where the angle is, the angle's up here, we automatically know that this is the hypotenuse. Remember, the hypotenuse is always opposite the right angle. Now that we have that out of the way, we need to label the other two sides, the other two legs of the triangle as opposite or adjacent. Since the angle's up here, this side would be referred to as the side that is opposite to the angle, and the remaining side, which is beside the angle, would be called the adjacent. Not to confuse you, but to just point out, both of these sides are adjacent to the angle. but this side already has a name. It's called the hypotenuse. So that's why it's not really a confusing issue about which side is the adjacent. Let's try one more. Okay, in this triangle, this is the hypotenuse because it is opposite the right angle. There's your right angle. And then this side is going to be the opposite side in terms of our notation. And finally, the leftover side here is the adjacent. So when I first learned this stuff, that's what I would do. I would label the opposite and the hypotenuse because they were the easy ones for me. And then the adjacent was the one that was left over. It's kind of lazy and indirect, but it got me through it when I first wanted to just make sure I got the right answers. And then afterward, I could get creative and think about it more deeply. So that's enough of that. We've labeled the triangles. We figured out how to do that. It's time to, and I'm going to emphasize this word here, define the ratios sine, cos, and tan. I want to emphasize that it's define. So if you're like, where did sine come from, or where did cosine come from, or tan come from? Well, the answer is someone decided to name it that. Now, I'm not going to get into a history lesson here, or a philosophy lesson, but that's pretty much it. So, definitions. Sine is defined as opposite divided by hypotenuse. Cosine is defined as the ratio of the adjacent side to the hypotenuse. And tangent is defined as the opposite to the adjacent side lengths. So these are ratios. So if you wanted to know the units of any of these, there are no units because the units would cancel. Let's say you had meters on the top here and meters on the bottom. That means that the units overall would be dimensionless. Sine would have no units. It is simply a ratio. There's just a summary of these three ratios. And you notice that I've actually just highlighted the first letter of each word and also the first letter of each of the side lengths for the ratios. So you see here SOH, and then you see CAH and TOA. So maybe this is overwhelming to memorize, but I remember back in the day when I was in high school, we came up with this. I didn't come up with it, but we were told about the acronym SOHCAHTOA. So now, if you haven't studied math the first time, maybe it wasn't in English, for example, maybe you didn't use the acronym SOHCAHTOA, but I do feel that from the many students from all over the world that I've worked with at the college, many of them have seen this acronym. So just remember there's three parts to it. So, which is for sine, ka, which is for cosine, and tan, or toa. So, like this last one here, just to remind you, this is tan, and then this is opposite and adjacent. See, tan is opposite over adjacent. So, we'll get into the nuances of what you're doing with this, but that pretty much is the beginning of this lesson. Now let's try to kind of put it together with numerical values. Here is an example on page 6 where we have a very famous 3-4-5 triangle. So if you've heard of that before, it's typically one of the earlier triangles that you see when you have right angle triangles. It's very nice because the numbers 3, 4, 5 work with the Pythagorean theorem, and they are simply just whole numbers. So no decimals here. And you know there are actually an infinite number of triangles that you can make up where the numbers are nice whole numbers. Some of them involve maybe you can double them. For example, 6, 10, whoops, that's a 10 there. It's supposed to be a 10. And 8. So if you double the sides, you have another one. And you could have other ones as well where they're brand new patterns. Just for argument's sake, you could have, for example, 5, 12, and 13. These are called Pythagorean triples, if you're interested. So if you Google or whatever Pythagorean triples, there are some neat relationships and formulas to generate an infinite number of them. But back to the question at hand here, we are simply looking for the decimal values for the three trigonometric ratios, sine, cosine, and tan of theta. So here's theta. So we'll do this one on a new page. and let's get going. So, oh, look at that, all labeled already. I took a little bit of time labeling because my handwriting here with the stylus might be too slow for you, and I don't want to bore you too much. Anyway, here's your hypotenuse. It's opposite to the right angle. And here is the opposite angle, opposite side I should say. Finally, we have the adjacent down here. So if we want to find the sine, cosine, and tangent ratios of these for this angle theta, well, there you go. The sine is defined as the opposite over the hypotenuse. And if you want to remember where we're getting that from, you could write at the top of this page here, SOHCAHTOA. So I'm simply using this shorthand to memorize or help memorize the three definitions. So if you look at sine, we have opposite to hypotenuse. So here's opposite and here's hypotenuse, and there it is, 3/5. I have decimal values here for these. Of course, depending on what you're asked, be careful to present the answer to the appropriate accuracy if necessary. Let's talk about cosine. So cosine is the adjacent over the hypotenuse. So that would be 4/5. There you go. And of course, 4/5 as a decimal is 0.8. Finally, you have tan of theta, which is opposite over adjacent. And in this case, opposite is 3 and adjacent is 4. Let's talk about the units a little bit here. So there's 3/4 or 0.75. I really want to emphasize here that the units right here are dimensionless. There are no units. And the reason there's no units on the ratio is because the inches here, or whatever units you have, would cancel. Even if the units were not consistent. Like let's say you had centimeters and inches, for example. Centimeters can be converted to inches or vice versa. So even if that was the situation, you still could have an answer that you should not have an answer that has units. Bottom line. All right. Now you can flip over to page 7. If you like, I would recommend you pause the video for this one and take a few minutes to do this one, because the information given in the question here is not 100% ready to calculate the value of cos of d. So you do need to do some extra stuff. So pause the video, give it a try, and then we'll resume. So here is the diagram, again with the information given. We want cosine of d. So you can see the first thing that I did here was I actually calculated the length of the hypotenuse. And I did that by finding, or using I should say, the Pythagorean theorem. Now, it says 42 there, but I should just mention that I actually got an answer that was 41.995 meters. So I rounded it to 42 for the presentation here, but you should keep extra digits if possible. In order to find cosine, think about what the cosine ratio is. Well, cosine, if I write SOHCAHTOA, what's cosine defined as? It is the adjacent divided by the hypotenuse. So in this case, it would be 38.4 divided by that number, or if you want a more accurate representation right here. So there's my adjacent and hypotenuse. Let's just fill in those numbers again because I felt kind of incomplete in how I presented the previous slide. So that's 41.995 meters. And I'll just put that on the diagram again here, 41.995 meters. So if we do the ratio here, we would have 38.4 meters, and I want to put those meters down, divided by 41.995. And to the prescribed precision in the question, the answer that I got was 0.914. That's consistent with the answer key. So hopefully that wasn't too taxing. I want to mention that when you're dealing with sine, cosine, and tan, you're not in practice going to need to use sine, cos, and tan for one triangle. At most, for any specific right angle triangle, you can get away with using sine, cos, or tan just once and still figure out everything on the triangle, all the angles, all the sides, depending on the context of the question and what information is provided. So just to say that again, you only got to use sine, cos, or tan once for a triangle, a right angle triangle. Here's another question. And getting on that point again, if you turn to page 8 here, this question is more of an exploratory question. It is not something that would be practically asked. No one's going to ask you to find sine, cos, and tan of an angle in practice for a triangle. Maybe one or the other, but not all of them. So we're going to go and calculate several ratios here. We're going to actually calculate 6 ratios. Sine, cos, and tan of P, and then sine, cos, and tan of Q. So we're going to get 6 ratios. Now that's going to take a while to do, but I recommend you pause the video, get a fresh piece of paper, and have at it. It should take you a few minutes. Something that I might do in class is give the students 5 minutes to do this as a self-check. So give yourself 5 minutes to do this. Pause the video and we'll resume shortly. So here I've presented the actual ratios at the end here for sine, cos, and tan of P. These are the numbers that you should get. I just don't want to drop those numbers on you, so I do want to show you how I obtain those values. And let's do that by just employing the Pythagorean theorem here. See, we need the side length here. So the way that we can find that side length, let's call that RQ. We'll just write here RQ. RQ is given by the Pythagorean theorem, uses the Pythagorean theorem. So we have here 5.71 squared minus 3.52 squared. Upon looking at your assignments, which were very well done, I didn't see too many issues with the Pythagorean theorem. Just remember here, this is not the longest side, so there is a minus sign in the equation. If you evaluate that, I got that to 5 significant digits. I like to keep a little bit extra because it is not the final answer. You should preserve some intermediate accuracy that is higher than or greater than the final answer. So let's calculate those ratios. So sine P, cos P, and tan P. I'm just going to write SOHCAHTOA up here. SOHCAHTOA. Starting with sine. Sine is opposite over hypotenuse. Perhaps we should write that side length here, 4.4960 inches. So sine is defined as the opposite over the hypotenuse. So opposite, well, we should label the triangle as well. Here's opposite, and here's hypotenuse. And the one that I always tend to kind of neglect a little bit is the adjacent. So for this angle P, remember the angle P is up here, we're pointing to that opposite side. That would be 4.4960. Whoops. If you're wondering, my computer processor is very, very, very alive right now while I'm recording these lessons. I guess it does a very demanding work on it while I'm recording these videos. Accurate to 3 decimal places, that answer is 0.787. Remember, there are inches here and there are inches there, and those inches cancel each other out. Let's just fix that equal sign, the approximate equal sign a little bit. Let's go for cosine now. So cosine is adjacent over hypotenuse. So in this case, the adjacent is a length of 3.52, and the hypotenuse is still 5.71. The inches cancel, and you get an answer of 0.616. So I'm not cheating. I'm not looking down here yet. I just want to point that out. I have my own work here on the side, and it's important that you're not passive and just reading an answer key when you're doing questions. Tan P, here we go. So tan is opposite over adjacent. So that is 4.4960 inches divided by, and the adjacent is 3.52 inches. So if we divide those numbers, we get 1.277. So that's pretty much the comprehensive study of all the ratios of the angle P. It's going to surprise you that I asked you to get 6 ratios. If you look back here, we have 6 of them to do. 3 up here and 3 down there. We've actually done 5 of them, not 6. And sorry, not 3. See, we have 3 out of the way. But what you're going to notice is that when we start to investigate Q, here's Q. The only change is that this becomes the opposite and this becomes the adjacent. The lengths are still the same, so if I just kind of look back in my notes here, that's still 4.4960 inches. The hypotenuse is over here, and that never changes. So I'm going to just flash back and forth on the slides here. See, this is adjacent, now it's opposite. And back to the original one here again. This is the angle P as a reference. Here's opposite, but relative to Q, it has become the adjacent. So there you go. So what you notice in the answer key here is that these ratios have a relationship, meaning that sine Q is the same as cos of P. Because if you think of Q, Q's opposite is what P's adjacent is, and vice versa. So I need only really show the calculation for tan Q, but I'll show all 3 of them just so that I'm thorough enough to explain things here. So sine Q, cos Q. So there is some redundancy here. I could cheat, but I'm not going to. So sine Q is the opposite, which is 3.52, over hypotenuse, which is 5.71. And when you do that, you get 0.616. And then cos Q is adjacent over hypotenuse, or 4.4960. And keep in mind, these are all inches, so if I'm getting a little lazy there, I apologize. The hypotenuse is 5.71 inches, and that gives us an answer of 0.787. What are the units here? The answer, there are no units. Okay, it is just a ratio. Tan of Q, opposite over adjacent, so this over that. 3.52 inches over 4.4960 inches. If you divide those out, you get 0.783. If you don't mind, I'm going to flip back to the previous slide. So here was tan of P. Let's highlight that in blue. See, tan of P is 1.277, and tan of Q is something totally different. But there's actually a neat little pattern here. If you take 1.277 and you take the reciprocal of that, you'll get the other answer. So I'll just make a note of that. 1 over 1.277. Of course, you are going to lose some accuracy. You're going to get that. And the reasoning is because when you look at SOHCAHTOA, tan is opposite over adjacent. And if opposite and adjacent are switching, it's like the fraction is going upside down. Here's our next example. This is one of the very famous triangles. It's called a special triangle. You may have heard of it as the 45, 45, 90 triangle. See? 45, 45, and 90. Because this triangle is so famous, it can be used, sorry, I should say that the triangle is famous because it can be used to calculate values for sine, cos, and tan of 45 degrees exactly. And by exactly, I mean without a calculator or any other type of reference. So we're going to go through that process right now. So I'm going to get the exact values of sine, cos, and tan 45, as well as show you how these decimal values are obtained. Before we do that though, it'd be useful if we knew what the length was here. So have a moment there and figure out the length of the hypotenuse. I'd like you to leave it as an exact value. So if I call the hypotenuse here x squared equals 1 squared plus 1 squared, because x is the longest side and the Pythagorean applies here. So you get x squared, I should mention x is equal to the square root of that. So x is root 2. So this side length here, without labeling it as x, is just root 2. If we're going to define the, if we're going to use the ratio sine, cos, and tan of 45, it would be useful to pick one of the angles. It doesn't matter which angle you pick, so just for argument's sake, I'll just pick that one there. So that would be the opposite, and that would be the adjacent. And of course, the root 2 is opposite the right angle, and that's your hypotenuse. So, according to the ratio of SOHCAHTOA, defined by SOHCAHTOA, sine, cos, and tan of 45 are going to be as follows. So you can write SOHCAHTOA here if you need the extra prompt. Maybe I'll write a little bit lower. So sine is opposite over hypotenuse. So in this case, opposite is 1 and hypotenuse is root 2. So that's 1 over root 2. Cos of 45 is 1 over root 2, again, because it is the adjacent over the hypotenuse. And tan of 45 is opposite over adjacent. See, opposite over adjacent. So that's 1 over 1. You could write these to 3 decimal places. And I'm just going to delete this decimal stuff here. We don't need the decimal part there. So 1 over root 2 is 0.707. This is actually a very useful number to know. It's very useful for many applications in mathematics and in physics to know what the decimal value is. To 3 significant digits is good for root 2 and for 1 over root 2. So I have those in the bank in my memory because I use them a lot, and especially when I'm doing geometry type and trigonometry type questions. So in your assignment that's forthcoming, I do put a question in there where you will need to use this special triangle and perhaps another special triangle, which is the 30, 60, 90. So there's another special triangle called the 30, 60, 90. It is analyzed in the notes, and I definitely am going to incorporate that in your assignment. I just want to make sure that you are aware that for your assignment, it's very important that you follow the instructions in terms of what I want. So if I say to you, please find the value of sine 45 exactly, what would be the exact answer? Is this an exact answer? Is this an exact answer? So the one that's exact is the one that you don't pick your calculator up for. This answer would be the exact answer. Of course, there are some small issues with it. In mathematics, it's not good procedure or presentation, I should say, to have a square root on the bottom. So 1 over root 2, little autosave there. 1 over root 2 can also be rewritten as something else. And I'll just show you here. You could multiply the top and the bottom by root 2 and get root 2 over root 4, or in other words, root 2 over 2. Now, why all the gymnastics here? Why isn't 1 over root 2 a nice number and root 2 over 2 is nicer? Well, the reason is that when you have a fraction on the bottom, that's an irrational number. And when you're talking about fractions are like when you want to share things among various destinations. Like if I say to you, for example, I'm going off on a tangent here, But if I say to you 3 over 2, or let's say 30 over 2, I could give you a real life question like, how do you give $30 to 2 people? Well, evenly, I should say. That's pretty easy. You just 30 divided by 2 is 15. Easy to do. But if I say to you, how do you give $30 to root 2 people? When's the last time you heard of having root 2 people? That's like 1.4 people. So having a denominator that is a whole number is very valuable in communicating what the fraction is describing. So let's talk about that calculator a little bit more. If you go to the notes, there are some pages 10 to 14 there where I start talking about trig tables. Now, trigonometric tables are somewhat historical, meaning that many years ago when people didn't have these calculators that we have that are super powerful and super cheap, they had to do all this stuff by hand, or they had to use other devices, and it was a lot of work. So having you look at tables was more of a historical and a learning experience, really to get your head around what people had to do a long time ago. And yeah, it's something to look at. I'm talking like 60 years ago, 50 years ago. So of course, with the invention of the computer and faster processing, this stuff using tables has somewhat become obsolete. But it's good to know and good to have in terms of your learning experience. So anyway, let's talk about the calculator a bit more. So what I'd like you to do is just grab your calculator and make sure that your calculator is set to degrees. Now, if you're not sure your calculator is in degrees, do me a little favor here. I want you to just type sine of 30 on your calculator. See that you get 0.5 or a half, okay? If you don't get that, your calculator is in the wrong setting. Your calculator might be in a setting called radians. Radians are another form of measuring angles, another unit system for angles, but we're not going to be using radians in this chapter. So make sure that when you type sine of 30, you get 0.5. Also on your calculator screen, you should see a button, or sorry, not a button, you should see a notification at the top of where your numbers are displayed that says D, or maybe it says deg, or something like that. If you have issues converting to degrees, probably 2 ways you can get around it. The cheap way is to just reset your calculator, because most calculators reset to degrees, or just look it up online with the model of your calculator. Okay, but it's in the menu somewhere. So it's not so much of an issue for us, because if you were in class and you were writing a midterm or something, the first thing I get to do is I just ask everybody to type sine of 30 on their calculator and make sure everybody's cool and gets the correct settings. So just grab your calculator and take a few minutes here, and I want you to evaluate these quantities. I'm not looking for any specific patterning. I just really want you to understand how to use the calculator. So this is probably the easiest calculation you're going to do for this lesson. So notice that it says here 4 significant digits if necessary. So I've done the calculations in advance. So if I make a mistake here, just tell me in the comments. But let's see if you got the same. So sine of 12 is 0.2079. And cos of 32 is 0.8480. Tan of 57 is 1.540. It said that for 4 significant figures if necessary. So this one, there's no approximate. Sine of 90 is exactly at 1. Now you might be wondering, how do I get a 90 degree when the triangle has 90 degrees already? Like, what I'm saying is, imagine you have a 90 degree triangle here. If this was 90, then this would be 0. So what the heck's going on there? Well, the idea here is that the sine of 90 is beyond the scope of a right angled triangle. It's a more advanced part of trigonometry where you extend the trig ratios, sine, cos, and tan, and other ones, to angles that are beyond 90 degrees. Okay, back to these calculations here. This one's pretty small. So cos of 85, I'm just waiting for my stylus to respond, 0.8716. There we go. And finally, tan of 22 is 0.4040. Okay. So there's some other motivation here for why I asked you to do these calculations. The main thing is that we noticed that tan can do some weird things. See here, tan? Tan's bigger than 1, and then here tan is smaller than 1. Can tan equal to 1? Be equal to 1? These are kind of questions that might be going through your head. Notice that no matter what I type for sine and cosine up here, I never exceeded a value of 1. So some interesting questions arise now. Can sine be greater than 1? Well, take a moment and think about that. That's a nice question, and it's straight from the notes too in terms of the homework exercises. So what do you think? Is it bigger? Can it be bigger than 1? The answer is no. Let's talk about why that's the case. The reasoning is that sine, remember sine is defined as, and I'm not going to use an angle theta here, I'm just going to write it in English like that. Sine is opposite. It'll take me longer to write it than to say it. Over hypotenuse. So, which is bigger? The opposite or the hypotenuse? Well, this one is always larger. At least on a right angle triangle it is. They only ever tie at 90 degrees. So, since the denominator is larger, or the numerator is smaller, you're always going to get a fraction that is less than 1, or in the worst case, equal to 1, but that's beyond a right angle triangle. So that's bottom line there, okay? The hypotenuse is larger. Hence, you get numbers or fractions like 4/5 or 7/9, but you'll never get something like 11/8. That can't happen because the denominator has to be larger. Can cos be greater than 1? Well, let's write down the definition of cosine. Cosine is adjacent over hypotenuse. Now, I'll ask you a very childish question here. Who wins? The top or the bottom? Hopefully you said the bottom, because the hypotenuse is always larger when you have a right angle triangle. So since the denominator is greater than the numerator, no, cosine cannot be greater than 1, because that would mean the adjacent would have had a larger value. So that's 2 out of the 3 questions that I have here at the end for you, philosophical questions. Interesting one here. Can tan be greater than 1? Let's write down the definition of tangent. So tangent is opposite over adjacent. Now, if you want to, kind of do something heuristic, which means just guessing, searching. See, look, tan's bigger or greater than 1 here, and then tan is less than 1 here. And if you go earlier, let's go back in time here, way back. Look at that, tan equal to 1. So you got everything. You got equal to 1 for tan. You got greater than 1. And you got less than 1. You got the whole thing. So basically, there are no restrictions on tan. Can tan be greater than 1? Sure. Yes. Tan can be whatever the heck it wants. Tan doesn't care if it had feelings. So anyway, that concludes the lesson for today, for this week, I should say. I think that the duration of the lessons, which I've tried to keep consistent over the first few weeks, has been good, and I've had good feedback from the students. The main thing is that there are places in these videos where I do like you to pause. And keep in mind, when we have class hours on the actual schedule, I am online, and I'm also online pretty much all day to answer your questions. I always have my email available. What I do want you to do, though, is double check that you have received a confirmation from me that I got your assignment, because I am still waiting on a few students for their assignments, and I need to get those assignments back to students, at least get the grades back, and post the solutions online so that we can progress. So if you haven't given me your assignment, or you haven't got a receipt from me that you got the assignment, that I got the assignment, make sure you do that. So for the next 2 weeks, we're going to keep on going with Chapter 5 and Chapter 6, and I will do a lot of application questions and really build up your confidence with trigonometry. I hope you have a lovely week. Take care.